Now, the last time we met, we had mentioned how when we have a three-phase current flowing through the stator windings, it induces voltages, and that voltage that is induced is able to generate a magnetic field within the stator, within the air gap. And we saw how this, and we something that I didn't mention is that if I have a phase current, if I have three phases A, B, and C, if I have coil A, coil B, and coil C, then the current flowing, if I have a balanced three-phase current, the current flowing, let's say through phase A, itakuwa the maximum. This is not the instantaneous current in phase A, coil A, will be the maximum current times the cos omega t. The current, instantaneous current flowing through coil B will be the maximum current times the cos of that, and the instantaneous current in phase C is the maximum current cos of that. Now remember that these phases, these windings are usually spaced 120 degrees, 120 electrical degrees apart. So you have a phase over here, a coil over here, we have a coil over here, and we have a coil over here. Let's say this is coil A, this is B, and this is C. They are 120 degrees apart from each other. Now remember this. I'm sorry. This is the current and the voltage are vector quantities. So when we plot them as a vector quantity, zitakuwa zina rotate. They are rotating about a fixed point. And when current moves, when we plot the path of current at different positions, when we plot the current at different positions, we are able, when we plot it as a graph, ndio maana tunapata a sinusoidal waveform. It's a vector quantity that has magnitude and that has direction, and it is rotating at an angular speed omega, and it takes time t to rotate. Now this is the phase angle of that current. How due to the 120 degrees electrical, so you'll find that there is one that is at 0 degrees. There is one that is on the opposite side of. If this is at 0, this will be negative 120, and this will be positive 120. But I just wanted to mention that this is the current of a balanced three-phase that is going through the stator winding. And then when this current goes through that stator winding, then it induces voltage. And now we want to see the value, or how to calculate the value of that induced voltage. Now, I'm sorry. Now, when a balanced three-phase current flows through the three-phase winding in the stator, a sinusoidal distributed magnetic field rotates in the air gap. Remember that, it is rotating at synchronous speed. Now, this rotating air gap will induce voltages in those coils, in those phase coils. This is not a distributed winding. This is a concentrated winding. But in my chora, I've drawn this distributed winding as a concentrated winding for easier explanation. So the rotating magnetic field in the air gap will induce voltages in these phase coils, and the flux density, the amount of the magnetic field lines passing through a specific point, a specific area. The flux density distribution, this is the flux density distribution, will be given by, in the air gap, will be given by the maximum flux times the cos of that angle. Will be the maximum flux times the cos of that angle. The air gap flux, per pole, which is denoted by P, will be given by 2 times the flux density maximum times L times R, where this is the axial length of the stator. when you take the length of the stator along its axis, axial length of the stator, and r represent the radius of the stator in the air gap. This is the flux density distribution in the air gap. This is air gap flux per pole. When we talk about flux density, is the amount of magnetic lines. Remember, when you have a magnetic field, this is, let's say we have a magnet there and another magnet there. These magnetic lines are what we refer to as flux. So when they pass through a point, an area that is perpendicular to the line of is perpendicular to the direction of the flux, what we get is flux density. So the flux density distribution in the air gap is given by the maximum density, flux density times the cos of theta, and this is the phase angle. Now, air gap flux per pole. Air gap flux per pole. Remember, when we have a number of poles in the stator, we have poles in the stator, the magnetic poles. Yeah. So when you want to calculate the amount of the lines of this, the value of the magnetism or this length of magnetic force in per pole, itakuwa the flux density, the maximum flux density times 2 times the axial length of the stator times the radius of the stator in the air gap. Now, the voltage induced in the first coil, for example, A, if you want to find the voltage induced in this phase coil A, the instantaneous voltage, the voltage at any instant, will be given by the maximum induced voltage times the sine of omega t. This is the speed at which that quantity is rotating in that magnetic field, and the time. This is the angular speed of the rotating magnetic field. Now, this is the voltage induced in coil A. The voltage induced in coil B will be E max sine omega t minus 120 degrees, and the voltage induced in C will be the maximum voltage induced in that coil, phase coil, multiplied by the sine of this. This represents the angular speed, and this represents the phase angle. Now, the RMS value or the total induced value per phase will be, the RMS value will be omega times the n times flux per pole, air gap flux per pole divided by root 2. When we open this in a 2 pi f, this is the omega. The angular density, the angular velocity is given by 2 times pi times the frequency of supply over root 2 times n times the air gap flux per pole. When you simplify this, you get that the RMS, or the total voltage induced per phase, is given by 4.44 Fn air gap flux per pole, where this n is the number of turns, number of series turns in that winding, and this is the air gap flux per pole. F is the frequency of supply. Now, what you have found is the induced voltages in the individual coils and the total voltage induced in per phase. Now, in an actual machine, you'll find that the phase winding, because it is distributed in a number of slots for better use of the iron and copper to reduce the losses, utapata kwamba that the value that we have gotten for the induced voltage over here, this induced voltage is equals to 4.4 times the frequency times the number of turns times the air gap flux. Because of losses in that state, you'll find that we have to introduce something known as the winding factor. The winding factor is introduced to cater in for the losses that we experience in the iron and the copper windings. Now, this winding factor, or the reduction factor, is usually 0.85 to 0.95, so that the actual RMS being induced per phase is 4.4 times the frequency times the number of series turns per phase times the air gap flux in that phase times now the winding factor. These winding factors will help you to cater in for the losses in the winding. So this is the total voltage induced per phase due to the rotating magnetic field in the air gap. Now, when the rotor, when the motor is at standstill, we consider, let's use the example of a three-phase wound rotor, induction motor, with the rotor that is left open circuited, meaning that there is no induced voltage in the rotor. So if the three-phase windings are connected to a three-phase supply, then a rotating magnetic field will be produced in the air gap. But since the rotor is not connected to that circuit, it is it's open circuited. That means that rotating magnetic field cannot induce a voltage in the rotor circuit. So that rotating magnetic field will be rotating at synchronous speed. Now this rotating magnetic field will induce voltage in both the stator. It will induce voltage in both the stator and the rotor. It will induce voltage in both the stator and the rotor windings at the same frequency. In this case, we will call it frequency 1. And the magnitude of those induced voltages in the stator and the rotor will be E1 will be the induced voltage in the stator, will be 4.4 using this formula up here. 4.4 times the frequency with respect to the stator times the number of windings in the stator times the flux per pole in the stator times the winding factor Kw1. And for the induced voltage in the rotor circuit will be 4.4 F1. We are going to call F1 F1 kwa sababu since the rotor circuit is not connected, then that induced voltage will be induced at the frequency of the stator. But the number of series windings in that rotor circuit will be different than that of the stator. So that's why we are denoting it as N2 times the flux per pole times the winding factor Kw2. Now, because these windings in a series in a wound rotor are usually similar, the winding material of the stator and the rotor are usually similar. So the induced voltage in the rotor will be the induced Kw1 and Kw2 will be equal. So we get this. Now, when we divide E1 divided by E2, the 4.4 will go. The frequency, since it's the same, will go. What you're left with is the number of turns, and the flux per pole is the same, so it will go. What you're left with is the winding factor and the number of turns. But since the winding material is made of the same material, so the winding factor in the stator will be the same as the winding factor in the rotor. Therefore, you get that the induced voltage in the stator and the induced voltage in the rotor, when you divide it, you will find that inakupatia something known as turns ratio. This is known as the turns ratio, and we'll see this mostly when we deal with transformers, because these induction motors work on the same principle as transformers. So when you divide the induced voltage in the stator divided by the induced voltage in the rotor, it should give you this ratio of the number of turns, series turn in the stator divided by the number of turns, series turns in the rotor, and this ratio is known as the turns ratio. But this now is operation at standstill. The rotor is not moving. At this point, the rotor is not moving. But now what happens when the rotor is moving? When you close that circuit, when the stator windings are connected to three-phase supply and the rotor circuit is closed, then the induced voltage in the rotor winding will produce a rotor current. We will introduce a rotor current which will interact with the air gap field to produce torque. Remember, we induce voltage in the stator. This induced voltage induces a voltage in the rotor. If that rotor circuit is closed, then a current is produced. And what happens when you have a current conductor in a magnetic field? That current conductor will have a magnetic field. If this is a conductor, kutakuwa na magnetic field around the conductor. And this magnetic field in the rotor circuit will interact with that the rotating magnetic field in the air gap, which is produced by the stator winding. And because of these two flux linking, these two magnetic fields linking, then a deflecting torque is produced, enabling this rotor which is connected to a shaft to rotate. Now, this is if this rotor is free, then it will rotate. Now, according to Lenz's law, this rotor will rotate in the direction of the rotating magnetic field in the stator. But remember that the rotating magnetic field in the stator is rotating at synchronous speed ns, and the rotating magnetic field, the rotor shaft, the speed at which the rotor is rotating, rotator at rotor speed, which is denoted by n. Remember, this speed is greater than this. There has to be that relative speed so that there is the induction, so that induction can happen. If these speeds are equal, then there won't be any induction. What happens then? The induced voltage in the rotor circuit cuts to zero. When it cuts to zero, then the speed will decelerate. Remember, what happens is this: as this magnetic field is rotating, this rotor will start increasing speed from 0 up to the point that it is the same as this speed. Ns at some point, ns will be equals to n. But when this point, when it reaches this point, then the induction in the rotor circuit will cut off, because there is no relative speed between the stator and the rotor. The rotor and the stator magnetic field, they are both rotating at the same speed. Yeah, so what happens? The rotor will decelerate, and once the rotor decelerates, then the induction, the voltage is induced again. That induced voltage in the rotor circuit produces a current which produces a magnetic field, and that magnetic field then interacts with the stator magnetic field, and the rotor continues to rotate. Now, that difference between the rotor speed and the stator magnetic field, which is rotating in the air gap, is what we term as slip. Slip is the difference between the synchronous speed of the stator magnetic field and the rotor speed. Now, if you are sitting, let's say this is the stator and this is the rotor. If you were sitting, you personally ulikuwa unakalia the rotor, you would see that this rotor inaachwa nyuma. It is slipping behind the rotating magnetic field in the rotor in the air gap. Hapo tunaelewana? I don't know if we are together in this class. Unajua mmenyamaza sana, so I don't know whether tuko pamoja. Are we together?
Yes.
You're too silent. Watu wamenyamaza ama watu wamewasha tu simu wakazima audio na video. Okay. Now, when you are sitting on this rotor, you'll see that the speed of the rotor is slipping behind the speed of the rotating magnetic field. So, if this is rotating at, let's say, 2000, and this is rotating at 1800 RPM, of course, kama umekalia hii rotor, utapata kwamba ni kama inaachwa nyuma. It's like it is going behind. So, this means that the rotor will be rotating at something known as slip RPM. The rotor will be rotating at something known as slip RPM, which is this SNS. It will be rotating at a speed which is the slip of which is S times the synchronous speed, which is now NS minus N. This is known as slip RPM. Now, the frequency of the induced voltage and current in the rotor circuit, when it is closed, will correspond to this speed, the slip RPM. because this is the relative speed between the rotor, the synchronous, the rotating magnetic field in the air gap because of the stator, and the rotor. So the induced voltage and current in the rotor circuit will correspond to this speed. Therefore, the frequency in the rotor circuit will be given by, remember how we find speed in this circuit. N is given by 120 times the frequency divided by the number of poles. Therefore, the speed in the frequency in the rotor will be given by P, which is the number of poles, multiplied by ns minus n, which is the slip RPM, divided by 120. This is when the rotor is closed. I mean, the rotor circuit is closed. By making F here, by using this formula and making F the subject, we get that F is given by n times the poles divided by 120. But in this case, our speed is not synchronous speed. It is the slip speed, which is ns minus n, to give us the frequency of the rotor circuit. And this is equal to P times the slip times ns over 120. Ile ambayo tulipata hapa. When we made S and S as the subject, it is equal to ns minus n. So we can replace this ns minus n with S slip times the synchronous speed. This is frequency 2. To give us that, F2 is the same as the slip times F1. Because frequency 1 is given, the frequency the frequency of supply in the stator, the rotating magnetic field in the air gap, will be given by the P times ns over 120. Yep. This here over here. If we are talking about the synchronous speed due to the stator winding, then this is referred to as the supply frequency because in the stator. So when you take these components, the P, the ns divided by 120, what we get is the frequency in the stator. Now times the slip. Therefore, the frequency of the induced voltage and current in the rotor circuit is the frequency in the stator circuit multiplied by the slip, where this F2 is also known as slip frequency. This is also known as slip frequency. Now, the voltage induced in the rotor circuit in the rotor circuit at slip S, when the rotor is rotating, will be given by 4.44 times the frequency 2 times the number of windings, series windings in the rotor circuit, times the flux per pole in that rotor circuit, times the winding factor, Kw2, which is given by 4.4. When you replace F2 with F1, you'll get that F2 is equals to SF1. So 4.4 times SF1 times the number of turns in that circuit times the flux per pole times the winding factor Kw2. Therefore, when you take this 4.4 times F1 times N2 times this, it will give you the value of E2. E2, remember, was the induced voltage when in the rotor circuit. This was the induced voltage in the rotor circuit when it was at standstill. 4.4 times frequency due to the stator times the number of windings in the rotor circuit times the flux per pole times the winding factor. What we have done is we have replaced the F2, the frequency induced in the rotor circuit, I mean the frequency of the voltage induced in the rotor circuit when it is moving, with this. And when you take 4.4 times F1 times N2 times flux per pole times the winding factor, what we get is the induced voltage in the rotor circuit when it is open circuited, times now the slip times S, to give us that the induced voltage. The induced voltage in the rotor circuit at slip S will be given by the induced voltage in the rotor circuit when it is not moving, when the rotor is not moving, times the slip. E2 is the induced voltage in the rotor circuit at standstill, at the stator frequency F1. Now, the induced currents in the three-phase rotor winding also produce a rotating magnetic field. Remember, once you induce a voltage in the rotor circuit, then this voltage produces a current, and those current, because we have the windings in a magnetic field, then a rotating magnetic field, rotor field is produced, which interacts with the magnetic field due to the stator, which causes the rotor to rotate. So the induced currents in the three-phase rotor winding will produce a rotating field, and its speed, the speed of that rotating field n, with respect to the rotor, the speed of the rotating field n2 with respect to the rotor will be given by 120 f2 divided by p. Sawa 120 f2 divided by p. This is 120 times sf1. Remember, f2 is slip times the stator frequency divided by p. Sawa. This gives you S and S. Okay. When you take 120 times the stator frequency divided by the poles, this will give you the synchronous speed of the rotating magnetic field in the air gap, ns, and times s, the slip, which will now give you the speed of the rotating magnetic field in the rotor circuit with respect to the movement of the rotor. Sawa. Any question up to that point? Kuna swali? Now let us attempt a question. I will project it sahi. Let me take a screenshot and then I send it to you. Nitatumia class rep and then awatumie ili muweze kuona kama mnaweza ifanya, ama tuipitie pamoja tuone kama tunaelewa. Hizo formula tumezielewa ama have you written them down somewhere?
Yeah,
lakini
tutaziangalia bado.
Okay. You can look at the books that I sent and then look at the topic of induction motors. You'll find a lot of examples over there ambazo mnaweza jaribu kuona kama you can be able to apply those formulas when calculating mambo ya three-phase induction motors. Let me send that picture haraka. Paul, you can share it with the rest of the
Okay.
Now the question is asking us to we have been given that we're told that a three-phase 460 volt 100 horsepower 60 hertz 4-pole induction motor delivers a rated output power at a slip of 0.05. So you're told to determine A, the synchronous speed and the motor speed. Now, we first list what we have. Let us first list what we have in that question. We are told that the supply voltage is for 60 volts. The supply voltage is for 60 volts. It's 100 horsepower. The frequency of supply is 60 hertz, and it is a 4-pole 3-phase induction motor, delivering a rated power at a slip of 0.05. So synchronous speed, how do we determine the synchronous speed? Ns will be given by 120 times F1 divided by the number of poles in that rotor. So we have stator frequency, which is 60 hertz. So the synchronous speed will therefore be 120 times the supply frequency, which is 60, divided by the number of poles, to give us that the synchronous speed, the speed of the rotating field, will be 120 times 60 divided by 4, 1800. Our synchronous speed will be 1800 rpm. Motor speed, what will be the motor speed? Remember that slip is given by the synchronous speed minus the rotor speed over the synchronous speed. We have the slip. We have been given the value of slip as 0.05. We have calculated and found that the synchronous speed is 1800 minus the rotor speed, which we are looking for, divided by 1800. So by making the rotor speed the subject, we'll get that the rotor speed itakuwa ngapi? When you calculate, what do you get the rotor speed as? (1710 rpm). You take this cross multiply with 0.05, 1800 times 0.05, unapata 90. So 90 is equals to 1800. 90 is equals to 1800 minus n. So n ukipeleka hii inakuwa positive is equals to, and take 90 to the other side, so 1800 minus 90 to give us that the rotor speed is 710 revolutions per minute. Sawa.
Yes.
Now the speed of the rotating air gap field. What will be the speed of the rotating air gap field? What will be the speed of that rotating air gap field? Nataka mniambie hiyo. What will be the speed of the rotating air gap field? Remember, we have been saying that the magnetic field produced by the stator rotates at synchronous speed. So what will be the speed of the rotating air gap field?
1800 rpm.
It will be 1800 rpm. You don't even have to calculate. You'll just write that the rotating field in the air gap will be the same as the synchronous speed, which is 1800 rpm. Okay, the third question, what will be the frequency of the rotor circuit? What will be the frequency of the rotor circuit?
I think we will have the same frequency of 60 Hz.
Remember that the rotor is rotating. This is the operation of this induction motor at when the rotor is rotating. So the frequency will have stator frequency F1 and we'll have rotor frequency F2. We have the slip. We have relative motion between the synchronous speed and the rotor speed. So that's why we have slip. Katika kuna formula tumeandika ya frequency. Where is it? That the frequency induced in the rotor circuit when it is rotating will be the slip times the stator frequency. So the rotor circuit, the frequency of the rotor circuit when it is operational will be the slip times the stator frequency. And the slip in this case was 0.05 times the rotor's the stator frequency, which was 60 hertz. Therefore, the rotor frequency itakuwa ngapi? 5% of 60.
3 Hz.
3 hertz. Sawa. When the rotor is rotating, then the frequency, this is known as slip frequency. But when it is standstill, the induced voltage in the rotor circuit will be at stator frequency when kama imesimama. But when it is operational and the rotor is rotating, then the frequency will be the stator frequency times the slip. What will be the slip RPM? This is another part of the question. What will be the slip RPM? What will be slip RPM? Remember when we say that when you stand or when you're sitting on the rotor will be in itakuwa inaachwa nyuma. So at what speed will that rotor itakuwa inaachwa nyuma na what speed? The slip RPM will be given by what? Remember we said that slip RPM, which is slip times n, the synchronous speed is given by the synchronous speed minus n. This is known as the slip RPM, and this is the speed. This is the speed at which the induced voltage and current are induced in the. This is the speed at which the frequency. This is the speed at which we get the frequency of the voltage and current induced in the rotor circuit when it is rotating, because we have to include the slip. So this slip RPM, if you're told to calculate the slip RPM, itakuwa the slip multiplied by the synchronous speed. Or you can take the synchronous speed minus the rotor speed. So slip RPM in this case itakuwa 0.05 multiplied by the synchronous speed, which is 1800 RPM, to give us that the slip RPM is 90 RPM. Sawa.
Yes.
Now that is wacha nitafute swali lingine hapa.
What about if you use the other formula
Of
120 times frequency over the number of volts? It will still give the same answer.
utapata hiyo.
Yeah, ukichukua 120 times frequency yenye tumeshapata frequency is equals to 3
utapata hiyo
over 4 volts.
You'll get it because that is the frequency at which the induced current, that is the speed at which that that rotor voltage and current are induced. So with that slip RPM, then you are able to determine the.
Yeah, it will still give the same answer, 90 RPM.
Okay.
Yeah.
Now let us. Now you're told that assume that. Let me look at this question. Assume that the induced. The rotor induced voltage at the operating speed. You're told to determine the rotor induced voltage E to S when it is operating. If the stator to rotor turns ratio is 1:0.5. Remember we said that when it is not operational, then the induced voltage in the stator and the induced voltage in the rotor will be given by when you divide them, it's the same as dividing the number of turns in the stator over the turns in the rotor. This is when it is at standstill, but when it is rotating, utapata ngapi? Because you've been told to find the rotor induced voltage at operating speed if the turns ratio N1 over N2 is 1:0.5. Now remember that this rotor, the induced voltage in the rotor circuit when it is closed is given by the slip times the induced voltage of the in the rotor when it is at standstill at stator frequency F1. Now when you look at this formula, E2 is the same when you make E to the subject upper. When you make E to the subject, it will be E1 times N2 over N1. If you are to make E to the subject. Therefore, when you replace the value of E2 with this in this formula over here, therefore the induced voltage, the induced voltage in the rotor circuit when it is operational, E to S, will be given by slip times E1 times N2 over N1. Okay. So 0.05 is the slip multiplied by the turns ratio. Remember that we have been told that the turns ratio is, so N1 over N2 is 1 divided by 0.5. Are you able to see my work? So N1 over N2 is 1 is to 0.5. Therefore, N2 or N1 will be 0.5 over 1. So a slip times 0.5 times 460, which is the supply voltage in the stator winding, E1. So slip times this ratio times the stator voltage E1, which is 450. This will give you the induced voltage in the rotor. Inakupatia that the induced voltage in the rotor is 11.5 volts. This is in the three phases, for the three phases. Now, if you want to find for per phase, if you want to determine per phase, then you'll take this 1115 and you divide by √3 to give you the induced voltage per phase. So the induced voltage per phase is 6.64 volts per phase. Sawa. Okay. So essentially what we have is you have those formulas utakuwa unaziapply to. I don't want you to derive. I'll never ask you to derive those formulas. But once you have the final formula, then you can be able to use those formulas to determine the induced voltage. You can be able to determine the synchronous speed, the slip speed, the frequency at which the rotor is rotating when it is at standstill and when it is operational. Now, when you looked at ile kazi ambayo nilikuwa nimewapatia ya kutafuta the break-in methods, I'm sure you found some terms like generating, plug-in, and all that. So because the three main methods, the three modes of operation of three-phase induction motors, kuna motoring. The motoring is the normal one. We have generating and we have plug-in. These are the three main, the three modes of operation of three-phase induction motors. Now, for motoring, when the stator terminals are connected to a three-phase supply, the rotor will rotate in the direction of the magnetic field. Why? Because sababu will have an induced voltage being induced in the rotor circuit, and if that circuit is closed, then a current is produced. That current will produce a magnetic field which will interact with the rotating stator field, and then this rotor will follow the direction of that rotating field in the stator because of Lenz's law. That is the normal operation of the three-phase induction motor, and this is known as motoring. You find that the speed of the rotating magnetic field in the air gap is greater than the rotor speed. the speed of the rotating field in the air gap is greater than the speed, the rotor speed. That is motoring. Now, the second mode of operation, generating. Now, if the motor speed is adjusted such that this speed, the rotor speed, is greater than the synchronous speed, and the system, the rotor is still rotating in the same direction as the magnetic field, then what happens? This induction motor will produce a generating torque. It will produce a generating torque, meaning that that torque will be acting in the opposite direction to the rotation of the rotor. So this torque opposes the motion of the rotor. We utilize this mode of operation, generating mode of operation, when we want to provide regenerative braking. Kwa mfano, when you talk about electric vehicles ambazo ziko na motor, electric motors, for them they utilize regenerative braking to return some of that, recharge their batteries. That power is, that braking is, that torque is converted to electric power, which recharges the batteries. Now, what do I mean? Suppose an induction motor is fed from, this is an example of generating mode of operation. Suppose we feed this, we are running this induction motor with variable frequency supply, meaning that I can increase or decrease the frequency at which I'm supplying my power. Meaning when I increase gradually from 0, then the speed of the motor will increase up to steady state. So when I'm feeding my motor from a variable frequency supply, the speed will increase. We do this to control the speed. Now, to stop the drive system, to stop that induction motor, then the speed is gradually reduced. In that process of reducing, the instantaneous speed of the rotor will be greater than the synchronous speed, because Bobo have reduced the supply of the stator. I have reduced the supply, the stator supply. So this speed, the synchronous speed, the speed of the rotating magnetic field in the air gap, will be less than the instantaneous at that point when I reduce that supply of the rotor speed. Now, this because of this, in that instant, this speed will be greater than this kwa sababu ya inertia. When you reduce this, it will reduce instantly, but kwa sababu of inertia, since the rotor is already rotating, haitasimama immediately. As a result, the generating action of the induction motor will cause power flow to reverse, and the kinetic energy of the system will be fed back to the supply. So that is how electric vehicles that have electric motors recharge the batteries by that generating torque. By that generating torque, and this is what we call, or this is what we term as regenerative braking. That is a very good example of the generating mode of operation. Now we have another mode of operation known as plug-in. Plug-in. Now what is plug-in? Now suppose I adjust the motor speed such that the rotating the rotor is rotating in the opposite direction as the stator field. So let's say the stator magnetic field is rotating like that, and the rotor speed is rotating like that. Now this will cause a braking torque. Here we had an opposing torque, a regen torque. Here we'll have a braking torque, which is in the direction of the rotating. It will be in the direction of the rotating stator field, but it will oppose the motion of the rotor. This torque is opposing it's opposing the rotor, but these two are still rotating in the same direction, but these are rotating in opposite directions. So the braking torque is still going to oppose the rotor rotating field, but the rotor rotating field is rotating in the opposite direction as the stator field. So it will oppose the motion of the rotor. So we utilize this when you want to bring this system to a sudden stop. Kwa mfano, when you have an induction motor running at a steady state speed, and we change the terminals of the three-phase stator winding, what happens? The magnetic field produced by the stator winding will change in direction as well. If we change two phases in that three-phase, then this will change. If it was rotating like this and then we change two phases, then the rotating magnetic field in the air gap will change direction. Now, unless Now what happens? The rotor will come to a stop. Why? Because these induction motors work on the principle of induction. When there's a magnetic field, the magnetic field induces voltage, voltage produces current, current produces a magnetic field, and these magnetic fields interact so that they can have a deflecting torque. Now, when this stator field changes direction, remember itasimama, and then once you change the phase, it will stop, and then it will start rotating in the opposite direction. So once that stator magnetic field stops, then the rotor will stop rotating. The rotor will come to a halt kwa sababu the stator magnetic field imesimama. But this rotor itasimama, then it will start rotating. It will increase it increase speed, but in the opposite direction. Unless now you cut supply to this kama when you change the phase of, let's say these are three phases, we have A, B and C. Ukatoa hii wire ukaweka hapa na ukatoa hii ukaweka hapa, so we can change the direction of the rotating field, so that when the motor starts rotating in the opposite direction, unless I cut off I remove these phases vile nimeziweka, then that rotor will continue rotating up to a steady state until I disconnect these phases. So even if remember, a three-phase induction motor is a self-starting motor. So even if I change direction, the motor will still rotate, but in the opposite direction. So we utilize plug-in when we want to stop this system suddenly. Are we together? If you're with me, please unmute and say that I'm present.
Yes, yeah, we did.
So you'll find this when you go through that assignment that I gave. You go find the break-in, how to control the speed of the three-phase induction motors. Now, the final thing that I want us to do today is I want us to determine the calculations of the equivalent circuits. We had looked at the equivalent circuit of a single-phase induction motor, and today we are going to look at the equivalent circuit of a three-phase motor. Ama tuangalie hiyo kesho. Do we do it now or tomorrow?
Tomorrow at what time?
Tomorrow we have a class in the morning, so you can let me know whether we can do it now or we can do it tomorrow in the morning. Do we continue ama tuendelee kesho?
We can continue.
Okay, now the equivalent circuit of a stator, of a three-phase induction stator itakuwa namna hii. And this is when it is at standstill. We have the stator terminals, we have the resistor, we have an inductor, we have the terminals at that end. So this is the current, the stator current, I1. We have the resistance in the stator, R1. We have the inductance in the stator, which is given denoted as X1, which is given by 2 pi F1 times L1, because this is a stator circuit. Then we have here IC, which is the core. This is now the rotor side. We have the magnetizing current, we have the core current, we have RC, which is the resistance in the stator, in the motor, and then we have the magnetizing reactance, which is given by 2 pi F1 LM. So this is the supply voltage V1, and on this side we have the induced voltage in the stator V1. So that is the circuit, the equivalent circuit model of a stator winding at standstill. Now we have, this is the stator. Let me differentiate between the stator and the rotor. We have the stator, and then we have a rotor circuit. we have the current I2 in the rotor, we have the reactance in the rotor at sleep, we have the resistance in the rotor, and we have the induced voltage in the rotor, which is given by SE2. Now, this here is the same as S2 pi F1 L2. Okay, now I'll give you a minute to try the two. We'll use this to calculate the power that is from the input power to the mechanical power, output power. We have to understand these circuit models. This here is the excitation current that causes the magnetic field to form in the air gap. And then we have the current that splits, that goes to the core losses, and then we have the magnetizing current in the stator. So we have the supply current that is being supplied to the stator terminals, and then we have the induced current that is induced here. This is the rotor circuit at sleep S. This side is the induced voltage in the rotor circuit. We have the current going, the rotor current. We have the reactance, which is given by S2 pi F1 L2. And then we have the resistance in that rotor circuit. Now, note that this, can I continue? Let me know whether I can continue ama kama naweza endelea. Can I continue? Hello, mnanisikia?
Sikia mwalimu.
Niendelee, mmechora? So this is the equivalent circuit of the stator, and this is the equivalent circuit of the rotor. Now note that this rotor, note that the rotor at sleep is at a frequency F2. The rotor at sleep is at a frequency F2. Now the rotor current I2 will be given by the voltage induced in that circuit divided by the resistance, and these resistances are in series. So R2 plus JSX2. Remember I told you in the other calculations, single phase induction motors, when we deal with reactances, then we have to include J because they are complex numbers. Now, since they're in series, then we add them. So remember, using Ohm's law, V is equals to IR. So the current will be given by the voltage divided by the resistance. The voltage in this case is SE2, and the resistance is R2 plus J plus that. Yeah. Now the power involved, the power involved in the rotor circuit. How do we determine power in normal instances? Power is given by I squared R. Power is given by VI. Power is given by V squared over R. So the power involved using this formula I squared R in this circuit will be given by the P2. The power in the rotor circuit will be I2 squared times R times R2. And this is known, this power is known as represents rotor copper losses. Rotor copper losses per phase. This P2, it is rotor copper losses per phase. Are you together? So Majamaa, msinyamaze sana.
Tuko pamoja.
Mkinyamaza sana bana nitashtuka. Nashangaa kaoni naongea peke yangu. Now look at this equation. This is the power. This equation is very important. So andika mahali. Hiyo yake kando. That is a very important equation. Now this equation ya current can be rewritten as I2 is equals to E2 over. Now if we divide the slip with every part hook, so itakuwa R2 over S plus J x2.
Tuoni hapo chini.
Pole. If we can relate this the current equation, the first one, by dividing this slip everywhere by S. And what we get is that the current, rotor current is given by this E2 over RS2 over S plus JX2. Now if we were to represent this as a circuit, itakuwa namna hii. If we were to represent this as a circuit, these are the terminals, we have the reactance, we have the resistance, and then we have, so this is E2. E2 is the induced voltage. We have X2, we have the current I2, and then we have this resistance now, which is R2 over S. Now I want you to see the difference between this circuit and this circuit over here. Now although the magnitude and the phase angle of current in these two rotor circuits are the same, although the magnitude and of this circuit and this circuit are the same, these two are different. Why? This first circuit here, the current I2 is at slip frequency. This is at slip frequency, or it is at frequency F2. Sindio? There is slip in this first circuit. But this current on this other side is at E2. And remember we said that E2 is the induced voltage in the rotor circuit when the rotor is stationary. So it is induced at stator frequency F1. So the current in the second circuit is induced at stator frequency. The current in the first circuit, this circuit, is induced at slip frequency. Now, in this case, the reactance, this leakage reactance, is dependent on speed, because sababu kuna slip SX2. So this leakage reactance is dependent on slip, but the resistance is constant. While in this case, the reactance is constant, but the resistance is dependent on slip. So if you were to calculate the power in this case, remember power is given by I squared R. So if you have to calculate the power, the per phase power in this circuit, itakuwa I2 squared times R2 over S. Are we together? The power in this second circuit will be given by I2 squared times R2 over S, which is the same as P2 over S. This I2 squared times R2 is P2, which we have written up juu. I2 squared times R2 is P2. It's P2. So when you take this I2 squared times R2 over S, when you take this I2 squared times R2, inakupatia P2 over S.
Yes.
Are we together?
Yes.
Now, you're told to calculate. You're given a three-phase 15 horsepower, 460 volt, 4-pole, 60 hertz, 728 RPM. Induction motor delivers a full output power at when a load is connected to its shaft. The windage and frictional losses of the motor is 750 watts. So determine a mechanical power developed. So what will be the mechanical power developed? Tuanzie hapo. Now, the full load shaft power So we have to change that 15 horsepower to kilowatts. And how do we do that? 1 horsepower is equal to 746 watts. 1 horsepower is equal to 746 hertz. So when the rotor sense is 15 horsepower, then the full shaft power will be 15 times 746 to give us that the total load power in that shaft itakuwa ngapi?
11.19 kilowatt
watts or 11.19 kilowatts. Now the mechanical power developed will be equal to the shaft power ambayo tumepata plus the windage losses. You get that? Now the mechanical power will be given by 1190 plus the windage losses, which were 750. Therefore the total mechanical power itakuwa ni 11,914 watts. Sasa umeona where those windage losses tunaziongeza ama tunazitoa. There are some questions that will tell you to ignore those losses. There are some will give you those losses, so you have to include them in your calculation. So you have been able to find the mechanical power developed. Now number 2, the air gap power. How do we determine the air gap power? Air gap power is given by I2 squared over S.
over S.
Now we have to, so what do we do? So synchronous speed will be given by 120 times F over P. We have to look for S, the slip. We don't have the slip in this case. So 120 F over P. So the synchronous speed is 120 over 60 divided by P, which is 4, to give us that the slip is
1800 RPM.
1800 RPM. Now remember that we are told that the load speed, the speed at which the rotor is rotating, was 728 RPM. And we have now the synchronous speed, the speed of the rotating magnetic field in the air gap. So the slip will be ns minus n over ns. And this is 1800 minus 728 over 1800 to give us that the slip ni ngapi? Our slip is 0.04. 0.04.
0.04.
Okay. Sawa. Now remember, I want you, kuna kitu nataka tukumbuke kidogo. Now the ratio at which these powers work, we have the P air gap as 1 is to S is to 1 minus S. So we had P air gap, we had P of the rotor copper losses, and we have P mechanical. Now we have calculated and we have found that the P mechanical is 11,940. So what will be the P air gap using these ratios? Remember that the ratio of the air gap power, the ratio of the copper loss power, the ratio of the mechanical power is 1 is to S is to 1 minus S. And we already have the value of the mechanical power. So we can also be able to calculate the ratio of, the power of the air gap power using this ratio. So 1 is to 1 minus S should give me should give me the air gap power. So 1 divided by 1 minus S, and our S is 0.404 is equal to 11,940 divided by the value of the air gap power that you are looking for. So the air gap power will be given by, when you cross multiply this, hii mambo ya ratio inachanganya kidogo. So yes, ni hiyo. So we will get that the P air gap will be 1 times 11,940 divided by 1 minus the slip 0.04 by utilizing these ratios. By utilizing these ratios, so the P air gap will be 11,940 divided by 0.96. Unapata that the air gap power is 12,437.5 watts. Sijui kama umeelewa hapo Paul. What we have utilized is these ratios. We got the mechanical power by adding the shaft power plus the losses, the windage losses 750. Tukapata that the mechanical power is 11,940. But utilizing this ratio 1:s is to 1 minus s, then we can be able to determine the copper loss power, and we can also be able to determine the air gap power. So by using this ratio, 1:1 minus s, and we have the value of s and we have the value of the mechanical power. This is the P air gap and this is the P mechanical. So 11,940. So what will be the value of the P air gap? Umeelewa hapo? Ama kuna swali?
Sina swali. Unavutia ratios tu hapo.
Ratios you can do it like this. But when we do it like this, this formula ambayo iko wapi? This formula over here, we can't use this kwa sababu we don't have the value of I2 squared. We don't have the value of the current, so what we use is these ratios to help us determine the mechanical power. So if I divide 1 over 1 by this, 1 by 0.04, no 0.96. It should give me the same as having the air gap power divided by when I divide the air gap power by this mechanical power, it should give me this ratio 1 divided by 0.96. So by making the air gap power the subject, then we get that the air gap power is 11,940 divided by 0.96, and this is 0.196 is 1 minus the slip, to get that the air gap power is 12,437.5 watts. Sawa. Now jaribu ya the rotor copper loss. How do you find P2 using the same ratios? We have that P air gap, the ratio yake na the rotor copper losses, na ratio yake na mechanical power is 1:s:1 minus s. You have the air gap power as 12,437.5. We have this as 11,940. So what will be the rotor copper loss? Itakuwa ni ngapi? So you can either use this mechanical power to get the copper losses, the rotor copper losses, or you can use this air gap to get the rotor copper losses. It will give you the same answer.
It's 497.5.
You get that the answer is 497.5 watts. Sawa.
Yeah.
And that's how you get your 8 marks or 9 marks. as long as you can be, you'll never be asked to derive these formulas, but as long as you have these formulas in mind, how to get synchronous speed, how to get kama these ratios, how these powers interact, the ratios of these powers, then you can be able to calculate these questions. Sawa.
Sawa.
So kesho we will look at some other examples, and then we'll pass through some few things, and we'll call this. Tutakuwa tumecover most of the things we expected to cover in this topic. Okay.